now it's my honor to present you Simon and his introduction to machine learning on edge.
Okay, good afternoon, everyone. Great to see you here. Today I will present our work on the adaptation of MobileNet for face detection that runs on edge devices, in this case an ultra-low power platform. And this is the work that I present on behalf of my colleagues, Dr. Engin Turetken, Professor Jean-Philippe Tirant, and Dr. Andrea Dunbar. So in this work, our goal was to implement a face detection algorithm that runs on a low-power platform. And by low power, we intend a platform that uses less than 1 watt from the acquisition of the data to the prediction. And our work is the adaptation of a lightweight network architecture for face detection specifically, and the study of optimization that we can use to further improve further reduce the computational efficiency. And then we deployed it on the low research platform, and we got an accuracy that is comparable to large models. In this talk, I will present the techniques used in the edge devices and face detection. Then I will present the training and optimization we selected for our model, and finally, the deployment pipeline. But first, maybe I will give you a bit of context. There is a huge problem of energy consumption in machine learning today. Since the beginning of the deep learning era in 2012, with AlexNet, the models have increased in computational complexity, and with it, the energy that they use to perform the predictions. And since 2017, with the rise of the transformers, we see that the computational complexity actually has increased at more than 10,000 times. So if we wait still 5 years, we will need 10,000 times more computational power to run our models on the cloud. So we have to find a solution. And one solution is to use edge computing. And edge computing provides several advantages: rapid decision-making in scenarios like, I don't know, autonomous cars, for example. You need to have fast decision in case of a pedestrian walking by. You don't want to send the data to the cloud and back. Efficient preprocessing also is a solution that is provided by edge computing, because you can process the data before sending it to the cloud, so you distribute a bit the processing across the devices. And finally, privacy-preserving applications. You can first transform the data before sending it to the cloud, or you can just perform everything on device, and you don't need any connection. So the data does not leave the device. And this has a huge potential. 1.8 billion devices are expected to run by 2026. But there are major challenges, which are energy consumption. And the energy consumption is mainly linked to the memory available. As you know, the memory exchange in devices are what consumes the more energy in these small devices. And finally, the computational cost is also linked to the energy consumption, because if you have a large number of operations, you exchange a lot of data with the memory, and hence you use more energy. So why did we choose face detection? There are a lot of applications. People counting is one, for example, to monitor the crowd in large areas or in retail centers, for example. Other processing like focus on cameras is one application of face detection. And finally, it's also an endpoint, an entry point for further processing, like face recognition, biometry. For example, on your phone, you first detect the face and then you recognize the person. The emotions tracking, and the tracking of the people in the street. Now I represent the techniques that we can use in edge processing and face detection. There are techniques to reduce the energy already, and there is a lot of research going on in this field. In the software side, you have optimization like pruning, which removes the weights of the model, quantization that reduces the bit precision of the weights of the model, and distillation, which is a technique that uses a large model, and you train a smaller ones to try to imitate what the large one does. Efficient operators, like separable convolutions, are optimized operations in the network that try to reduce the computational complexity or the size of the weights. And finally, event-based processing, like spiking neural networks, use sparse data representation to further save energy, because if you have sparse data, then you don't need much computation. On the hardware side, there are a lot of improvement in the silicon processing, like FinFET. You may be aware of the FinFET technology and fully depleted silicon on insulator process tech. Resource optimization, like power management, is also a focus for engineers that work on these devices. You can just turn on the device when you need to do the processing, or you can just turn up some of the elements of the device. Specialized units, like convolution accelerators or zero skippings, are also optimization that you can have on your devices. And finally, event-based processing accelerators, like the neuromorphic hardware of Intel, the Loihi, IBM Thrunos, Spinnakers. These special hardware are aiming at processing spiking neural networks, which process sparse data, so you can further reduce the energy in that case. Today, I will just focus on these three highlighted techniques, quantization and efficient operators, in order to exploit the specialized units that is available in our hardware. So let me first speak about the quantization. You can have two paradigms in quantization. Either you can select a distributed quantization based on the distribution of the weights, where you sample and try to cluster the weights at some precise interval. In this case, I show the uniform in purple and the logarithmic sampling of the weights. Or you can have a rounding quantization where you try to round the values to the nearest one. And in this case, I show the Q values, which uses a certain number of bits to represent the weights and to represent the integers, and the rest of the bits to represent the floating point value. So you get some roundings that are represented in this graph. Now, if I present the efficient operators, there are operators that have been developed since 2017 and 2018. In that case, I exploit the separable convolutions that are shown on the right. These special convolutions try to factorize the kernel of the convolution into not matrices, but two vectors. So you save the space of the matrix. And if you use, then you can basically, by performing this depth-wise convolution and then the convolution with a one-by-one kernel, you can reobtain the representative power of this, almost the representative power of a full convolution. And there are two flavors of this. You can have either one combined with a skipped convolution or one that is strided. And these are presented in the MobileNet-V2 paper. And these are the operators I used in our work. But I just show also another one that to show that there is other techniques that exist. This one is the shuffle-net block, where you do a grouped convolution, then you shuffle the number of channels, and you perform the convolution afterwards. So there are a lot of optimization going on in the field. Our selected architecture is the MobileNet-V2 that exploits the two first blocks I presented just before. And this MobileNet is available directly from Keras, and you can load it with pre-trained weights on ImageNet. It has some interesting features, like the number of separable parameters is almost equivalent to the square root of equivalent convolutions. So if you use separable convolutions instead of normal convolutions, you have the square root of the number of parameters and computations. And there is also an alpha parameters that allows you to select the number of channel width of your model. If I now present the techniques for phase detection, Face detection is actually an old task in machine learning. It started way before 2001, but in 2001 there is the small, I would say the ancestor or the old filter-based technique used on presented in the work of Euler and Jones, called the hard features, and it's a bit what is happening today in deep learning. You use filters and convolution, and you observe the response of the filters to detect the face, and you have almost response that are equivalent to this image below, and the work of Jan and colleagues in 2014. And in 2017 and 2016, the model performing face detection were mostly based on the separation or detection of few features like the eyes, the mouth, the nose, and try to combine it to detect where is the face. The one we selected is Tiny Face, which is a work presented in CVPR in 2017. And this work actually uses 3 resolution of the same image that passes through a CNN, in this case a ResNet, and output a feature map to detect the face. And it outputs this map at each resolution and predicts the bounding box associated with the heat map. Then we use a non-maximal suppression algorithm to find the final prediction. Now let's see how we can exploit this in our work. We chose an iterative optimization. First, we select the architecture by exploring a bit how it works. Then we quantize it to further reduce the complexity. Then we use the feature presented in MobileNet, which is the width selection of the number of filters. And once we have optimized all of this, we can finally go to the deployment. So as I presented, we selected the tiny face architecture, but the ResNet is too big to run in the device. So we replaced it by a MobileNet-V2, and then we further optimized the MobileNet-V2 to further reduce its complexity. So the first thing is to select the output. Here I show a few output that we selected, so we can cut the network at point A and B and combine the output in different ways. And the number 63, 98, 133 presented in the table 1 represent the number of layers that are fixed before retraining. So if we load the MobileNet with the features from ImageNet, then we retrain at that point. And if we look at the table, you can see that the A98, so the one that cuts the network a bit before and trains only a few layers, is the one that performs the better. Now that we have explored the architecture and selected where we want to cut the network, we can quantize it. In that case, I used the Q representation, as mentioned in the introduction. And here we can see that the accuracy is almost maintained until you use 7 bits of precision, because actually the range of the weights are not representative, cannot be represented using only 7 bits of integers. If you go even lower using 6 bits, then you lose a lot of information, and the network actually can't learn anything. The average precision, just to mention, is the score we use to score the face detection performance, and it's the overlap between the true bounding box and the predicted one. Now that we have selected quantization, in that case, FP, we can see that Q9 is almost near the FP32 and FP16 representation. We can go to the width selection, and the width selection reduces the number of filters, like shown on the left. And we can see that it highly impacts the performance. If we use the A98 model, which was the first model selected, and we reduce the number of filters, we can see that the performance decreases. But we can see that the A98 model with 0.5 value of alpha, so half of the number of filters, still performs better than the other models like B133 and C98. And it also has way less parameters. So now we have gone through our entire optimization process. We can now select the model. And here it's a summary of the models we trained. And as you can see, the one that we selected is the A98 with the alpha equals 0.5, so half of the number of filters, because it's actually the only one that fits in our small device. But as you can see, it still has fine accuracy. It's not state-of-the-art, obviously, but it's still close to the ResNet and better than the classic ML algorithms like Viola-Jones. Okay, now let's go to the deployment. So the deployment process is quite hard, actually. We had to do several iterations to manage to implement this model on the device. So starting from our model trained with Keras, we can convert it to TensorFlow Lite. Then we use tools provided by the platform, like NNKs, that further transform the model in order to make it compatible with the device. And the device that is present here, you can come afterwards to, I can show you a demo. Actually, I don't have a camera here to show it, but you are welcome to try it afterwards. This small device has a MicroPython environment that runs on it. So you can just load the model, then we run this MicroPython script to do the prediction that is visible on the LCD screen. And here I show a few examples. I can't measure the accuracy on this device because the memory is too small, so I can't transfer the dataset on the device to perform the accuracy measurements. So that's why I just present a few empirical results or qualitative results, but that's actually a future work. So in conclusion, we have shown that the MobileNet-V2 can be adapted for a face detection purpose, and that it's better than classic face detection like the Viola-Jones that can run in some of the devices today. So using this accelerator for deep learning is quite a good advantage. We perform an iterative study of optimization to allow the deployment on the edge device. So it's quite a long work and a lot of effort still to optimize these models to make them compatible with the devices. And the next steps are measuring the accuracy and consumption of the deployment platform, as mentioned. Then deploy other models like the Q format. Improve the quantization and optimization schemes, so we can further improve or further reduce the complexity of the model, obviously. Even selecting another network should be advantageous. We also want to explore dynamic width adjustment, so you can change the width of the number of filters based on the complexity of the task you're doing. So we will have a dynamic power consumption. And finally, compare with other platforms like the CSEM Visage chip that we are developing in-house. So that's it. Thank you.
Thank you, Simon. Thank you very much. Thank you for your presentation. Other questions in the audience? We have roughly 5 minutes for Q&A.
Yes.
There are two. Maybe you first, because then Gabriel has to walk less.
Hello. Thank you for the presentation. I have a question regarding the quantization. Where exactly and how did you apply it? Was it similar in the forward pass, backward activations, weights? Like, did you change a bit the quantization depending on where it was in the network?
It would have been a good strategy to apply it during training, but actually what we did is just perform the quantization after the training. So you have your network with the weights, and then we just transform it to integer representation in order to make it compatible with the devices. But definitely that would be a good strategy to train it, to do quantization-aware training so that you can quantize the network during the training and maybe change the quantization between the layers. But for the moment, it's just uniform quantization across the layer. Welcome.
Yeah, thank you for the nice presentation. I have a question about one of the slides that was related to width selection, where you have used the different values for alpha. So, yeah, the previous slide, yeah. So here we can see that for model A98, we have different values for alpha, like 1.0, then half of 1, 0.5, and then 0.35. So we can see a jump, not a specific pattern. So how you came up with these values, whether there was some search space you have utilized or randomly selected?
No, actually, that's the... the MobileNet is available in Keras, so you can load it, and the pre-trained weights from each ImageNet are only available for these values of alpha. But you can definitely train the model from scratch and using an arbitrary value for alpha, even, I don't know, 0.73 or something like that. But these are the ones that are available or made available by Keras with the pre-trained weight.
Further questions? I have one, Simon. So you have presented a solution where you don't need a lot of space, not a lot of energy. It's a small device, but where do I use it?
So
what's the use case?
You can expect edge computing to occur actually a bit everywhere, especially in the Industry 4.0, which is one of the targets of CSEM. If you have a device that is monitoring industry components, then you don't want to spend a lot of energy or having a huge GPU server running just near your device, actually, to do the predictions. And otherwise, all the smart watches that have a very low power and low processing capability, then you can have powerful models that can run in this, and you can do obviously predictions on the health or monitoring that is a bit more complex. That is what is done today.
Okay. Thank you very much, Simon. Yeah, one more round of applause.
Thank you. Thank you.
Here you go.
Thank you very much.
Stay hydrated in summer.